Hi, ladies and gentlemen. This is Mr. Green, and we're taking up another topic in the field of geometry. Once again, we're looking at some geometric issues. This is one that I think is very, very interesting, and has just been recently come up as a more important topic. And think you'll see why when we get into it a little bit more. Don't forget, you can be making quiz corrections and due dates. We're getting close to the end of the semester. These things are going to be very important. Get your grade up. So you want to make certain you get them accomplished, okay? So what are we talking about here? We're talking about graph theory, okay? So want to make certain we define just a couple of things to begin with. If I'm looking at the edge of a set of graphs like this would be called a vertex or an edge. I'm sorry. It'd be called an edge, E-D-G-E. Okay? And this one up here, while it's curved in nature, would make that not an edge, but a bridge. Because it's bridging two points together. Okay? It's not a natural polygonal type connection between the two. Now I want you to notice, I've got two other points that are identified here. I've got point L and point H. Point L, I've got one edge coming into it here and an edge here coming into it. So that one has a degree of 2. This one, I've got 3 lines coming into it. So that one has a degree of 3. The degrees are going to be important, so we want to make certain we understand these. So if I'm looking at this type of an object over here, AG is going to be an edge, but BC, see how it's curved like that, is going to be a bridge. It doesn't matter which BC you're looking at, the one going above or the one going below. Let's look at some degrees here. At point A, how many lines do I have coming in there together? I've got 3. At point B, how many lines are coming together there? I see 3. Let's count them. Make certain you see them. I see 1, 2, and 3. All 3 of those would be coming together. That would make a degree of 3 there. For C, I see a 3. For D, I see a 3. For E, I've got a 2. For F, I've got a 2. And for G, I've got a 4. So I've got several odd numbers and a couple of even numbers there. Wonder if this makes a difference for what we're going to do. A Euler path. A path here is a way, a Euler path is a way that we could traverse from point A to point D and go through each point only once. We don't want to have to repeat ourselves or go down each path only once, okay? So if I went down F and up G and down E and up D, up this way, over across this way, up and over, and then down through this way, did I hit each path? No, I didn't hit this path up here, did I? Not really possible in this situation. Why? Well, it turns out that the issue is right here. I have too many odd numbers. Okay? And if I drew a line from B to C going across like this, that would make this have a degree of 4, and this one would have a degree of 4. Then over here, I could go from A to D and only touch and go on each path just one time. And I'll show you here. Wow. Touched each path only one time. Why would this be important? You know what? Think of this as the ice cream truck. The ice cream truck. Why? The ice cream truck travels around and it goes down every street and it rings its bell and sells its ice cream, right? But it doesn't want to have to go down a street more than once because that would be wasteful in gasoline. That would be wasteful in time. And so it tries to draw a Euler path so that it only goes down each path one time. Okay? There are other examples, but that one works. Okay? A Euler circuit, on the other hand, wants to wind up at the same point that it started at. Why? Well, that same ice cream truck doesn't want to start in New Jersey and wind up in New York City. And if we followed this one here, we could get a Euler path out of it, but we started at A and wound up at D. Notice how when we add a bridge from A to D, now it comes back and it starts at A and ends at A. That would be a circuit. That would be a Euler circuit. The whole point here is it winds up back at the place where it started and it doesn't have to worry about it. That's what we are talking about when we're talking about Euler paths and circuits. Okay? A Hamiltonian circuit, however, is one where you want to go through every point just once. Why? Well, it doesn't matter if you're going down every path. It matters if you're going to every point. If you had a salesman, making certain that that salesman hit every point. If you'll notice what I did over here in the Euler paths, here, I went through this point twice. I went through this point here twice. I went through this point 3 times. I went through this point 3 times. So those wouldn't be good concepts in a Hamiltonian path, okay, or a Hamiltonian circuit. You want to go through every point just one time, okay? The definitions of circuit and path are still the same, but I want you to see here. I just did a Hamiltonian circuit. Could have done the same thing on all of them. Why? Because I only hit each point one time. Okay? Okay. Okay. Had slides in here twice. Sorry. So, I appreciate you making certain you send me questions. Okay? Make certain you tell me that you're in geometry. And I look forward to seeing you at tutorings on Tuesdays, Wednesdays, or Thursdays. And remember, we're getting close to the end of the semester, so get everything taken care of that you can. I look forward to talking to you next time.